Hi students, let us learn about applications of Gauss's law in this session. We already learned about electric flux in video 4. What is electric flux? Electric flux phi E is equal to E dot A, or electric flux phi E is equal to EA cos theta. Gauss law is used to find out this electric field. First, we will learn to find the electric field due to an infinitely long, straight, uniformly charged wire. Let this be a uniformly charged wire. It is an infinitely long, straight, charged wire, positively charged wire. Since this is infinitely a long wire, you need some surface to explain the electric flux, isn't it? So we will consider a small cylindrical surface on this charged wire. This is the Gaussian surface. This is the cylindrical surface which you are considering, and this is the infinitely long, uniformly charged wire. Let L be the length of this cylinder and R be the radius of the cylinder. What will be the curved surface area of this cylinder? It will be 2 pi R L, where L is the length and R is the radius of the cylinder. To find out this electric field E, you have to find out the electric flux passing through this surface. This cylindrical surface has two end faces and this curved surface area. The electric field E will be normal to the surface. The electric field, if you draw, this is the surface and it will be normal to that surface. We have to find out the electric flux through this Gaussian surface. This Gaussian surface has two end faces and a curved face. How can you draw normal to this end face? Normal will be perpendicular to that face. This is how you draw normal to that face. For this face, the normal will be in this direction. For the curved surface, the normal will be in this way. First, let us consider these two end faces. What is angle theta? Theta is equal to 90 degree when you consider the end faces. This is the direction of electric field and this is the direction of the area vector A. This one and this one, E and N, are perpendicular to each other. Therefore, phi E becomes 0. Cos 90 is 0. That is, the flux at these end faces are 0. There is no flux or no electric field at the end faces. You have to find out the electric flux only on this curved surface. For the curved surface, E and N are shown in the diagram. Therefore, theta is equal to 0, cos 0 is 1, phi is equal to E dot A. What is A curved surface area? A is 2 pi RL. Therefore, E multiplied with 2 pi RL will give you the electric flux through this curved surface. Theta is equal to 90 degree for side surfaces. Cos 90 is 0. Therefore, phi is equal to 0. Flux through the two ends of the Gaussian surface is equal to 0. Flux through the Gaussian surface is equal to E into 2 pi RL. That is, curved surface area of the cylinder is 2 pi RL. Now we have the equation, general equation for electric flux phi E is equal to E into 2 pi RL. But according to Gauss law, phi E is equal to Q by epsilon naught. We learned this in Gauss law. What is this Q, the charge enclosed? Since this is an infinitely long wire, we do not know about the charge which is enclosed within it. As this is an uniformly charged wire, we will take the linear charge density lambda. Lambda is equal to Q by L. Linear charge density means charge per unit length. Therefore, what is Q? Q is equal to lambda into L. Please remember the formula, lambda is equal to Q by L, where lambda is the linear charge density. And you can replace this Q with lambda L. Therefore, phi E is equal to lambda L by epsilon naught. You have two equations for phi E. Phi E is equal to E into 2 pi RL and phi E is equal to lambda L by epsilon naught. The first equation is the general equation and the second equation is as per the Gauss law. Equate these two equations, equation 1 and equation 2. LHS is the same. You can equate the RHS. Therefore, E into 2 pi RL is equal to lambda L by epsilon naught. L and L you can cancel on both sides. You need to find out E. Therefore, take this 2 pi R to the right hand side. What is E? E is equal to lambda by 2 pi R epsilon naught. This is the expression for electric field. Remember this expression for electric field for an infinitely long straight uniformly charged wire. E is equal to lambda by 2 pi epsilon naught R. Now let us study about an infinite plane sheet which is uniformly charged. We are going to find out the electric field of an infinite plane sheet. This is the diagram of an infinite plane sheet which is uniformly charged, as you can see from the diagram, and these lines represents the electric field. We know the electric flux phi E is equal to E dot A, or electric flux phi E is equal to EA cos theta. To find out this electric flux, we need the Gaussian surface as before. In this case also, we will consider a cylindrical surface as the Gaussian surface. We know that the electric field will be always normal to this surface. The normal to the surface means the electric field will be in this direction. What will be the electric flux through these two end faces? Normal to this face will be in the same direction. Therefore, flux phi is equal to E dot A, because cos 0 is 1. Since you have two faces, the total flux will be 2 times EA. What will be the electric flux through this curved surface? The electric flux will be 0, as E and A are perpendicular to each other, because normal to this curved surface will be in this direction. When E and A are perpendicular to each other, theta is equal to 90 degree and flux becomes 0. In this case, for infinite plane sheet, you don't have to find out the electric flux through the curved surface. You need to find out the electric flux only through these two end faces. Electric flux phi E is equal to 2 times EA, because you have two n phases. And phi E is equal to Q by epsilon naught according to Gauss law. What is Q? Q is the total charge enclosed, and here this is an infinite plane sheet. We don't know about the total charge. Therefore, you have to write down the surface charge density. What is surface charge density? Surface charge density is sigma, denoted by the letter sigma, and sigma is equal to Q by A, where Q is the charge and A is the unit area. Charge per unit area is known as surface charge density. You can replace Q with sigma A. Surface charge density sigma is equal to Q by A. Please remember this formula to proceed with. Phi is equal to sigma A by epsilon naught. This Q is now being replaced with this sigma A. Therefore, you will get phi is equal to sigma A by epsilon naught. This is the first equation, which is the general equation, and this second equation is as per the Gauss law. In these two equations, LHS is the same. Therefore, you can equate the RHS to EA is equal to sigma A by epsilon naught. You need to find out electric field from this expression. E is equal to sigma by 2 epsilon naught. A and A gets cancelled. This is the expression for the electric field for an infinite plane sheet which is uniformly charged. E is equal to sigma by 2 epsilon naught. This is the electric field for an uniformly charged infinite plane sheet. For an infinite plane sheet, we will use the letter sigma, which is the surface charge density. Whereas in the previous case, when we learned for an infinitely long straight wire or a straight conductor, we use the notation lambda, which is the linear charge density. Finally, we can learn about the electric field of a thin spherical shell. This spherical shell is also uniformly charged. This is the shell which is uniformly charged. You can see the charges are on the surface of the shell. When we learn shell, remember the charges are on the surface of the shell. There will be no charge inside the shell. Let capital R be the radius of this shell. Here we need to find out the electric field outside the shell and inside the shell. First we will learn the electric field outside the shell. For that, consider a point P outside the shell and you draw a Gaussian surface. This is the Gaussian surface, which is a sphere outside this shell. This Gaussian surface is also a sphere. Let small r be the radius of this sphere, the distance from the center to the Gaussian surface. It is indicated by the small letter r. The electric flux phi E through the Gaussian surface is phi E is equal to E dot A, or phi E is equal to EA cos theta. Say this be the point P and this will be the electric field. If you consider any point on the surface, the electric field will be perpendicular to that surface. Normal will be also in the same direction along the radius. Angle between E and A is 0. Therefore, cos 0 is 1. Phi is equal to EA. E into A. A is 4 pi r squared. Small r is the distance from the center to this Gaussian surface. This distance is indicated by small letter r. The electric flux phi E through this Gaussian surface will be E into 4 pi r squared. According to Gauss law, phi E is equal to Q by epsilon naught. Here we have to consider the surface charge density. Sigma is equal to Q by A. The general equation phi E for the outside the shell is phi E is equal to E into 4 pi r squared. Sigma is equal to Q by A. Q by A. A is equal to 4 pi r squared. Please note here you are using the capital letter R. Sigma is equal to Q by A. Sigma is the surface charge density and the charges are on the surface of the shell. If this is the shell, the charges are residing on the surface of the shell and the radius of the shell is capital R. The charge is on the shell. Therefore, when you are considering the surface charge density, you must consider the area of the shell. That is why you are using capital R in this expression. Phi E is equal to Q by epsilon naught according to Gauss law. Phi E is equal to, in this place of Q, now you can replace with sigma A. Sigma A is equal to Q. Q is equal to sigma A. Sigma into A is equal to 4 pi r squared divided by epsilon naught. Now you have two equations for electric flux phi E and you can equate those two equations. Since the left hand side is the same, you can equate the right hand side. Therefore, E into 4 pi r squared is equal to sigma into 4 pi r squared by epsilon naught. You need to find out E from this expression. Cancel 4 pi and 4 pi. Therefore, E is equal to sigma by epsilon naught into r squared by, bring this r squared to the other side. Therefore, E becomes sigma by epsilon naught into r squared by r squared. This electric field expression can also be written as Q by 4 pi epsilon naught r squared, because we know that sigma is equal to Q by A. Q by A is 4 pi r squared. R squared and r squared get cancelled and this expression becomes Q by 4 pi epsilon naught r squared. You can remember this expression for electric field, or you can remember this expression, either this one or this one. This is the electric field due to an uniformly charged thin spherical shell. And for outside the shell, the expression is sigma by epsilon naught r squared by r squared or Q by 4 pi epsilon naught r squared. Let us find out the electric field due to an uniformly charged thin spherical shell for inside the shell. This is the shell and charges are residing on the surface of the shell. We need to find out the electric field inside that shell. To find out the electric field inside the shell, you need to draw the Gaussian surface inside the shell. Consider any point P and draw the Gaussian surface. This is the Gaussian surface. And let R be the distance from the center to this Gaussian surface. Small letter r is the distance from the center to this Gaussian surface which is inside the shell. We have seen that the electric flux through the Gaussian surface is phi E is equal to E into 4 pi r squared. For a shell, there will be no charges inside the shell. All the charges are on the surface. Now, the Gaussian surface is inside the shell And will there be any charge inside this Gaussian surface? No, there will be no charge as there are no charges inside this shell. Q is equal to 0. According to Gauss law, phi E is equal to Q by epsilon naught, which is equal to 0 as there is no charge inside this Gaussian surface. Let this be equation 1 and this be equation 2. You can equate the first equation and the second equation. That means E into 4 pi r squared is equal to 0. 4 pi and r squared cannot be 0. Therefore, E is equal to 0. What is the electric field inside the shell? It is 0. In this case, for spherical shell, thin shell, let this be the shell. We considered a point outside the shell and inside the shell. Inside, you found electric field to be 0. And outside, the expression for electric field is Q by 4 pi epsilon naught r squared. In this session, we learned about the applications of Gauss's law. We already learned Gauss's law and we know to find out the electric flux. In the applications, we learned to find out the electric field due to an infinitely long, straight, uniformly charged wire. We got the expression as E is equal to lambda by 2 pi epsilon naught r in that case. Then we found out the electric field due to uniformly charged infinite plane sheet. Then E is equal to sigma by 2 epsilon naught. Lastly, we found the electric field due to a uniformly charged thin spherical shell. In that case, we considered the electric field outside the shell and inside the shell. E is equal to Q by 4 pi epsilon naught r squared outside the shell and E is equal to 0 inside the shell. I hope you understood the session. See you.